All right, yeah, thank you very much, Philip, for the kind introduction, and it's a pleasure to be here with the Southeast Coastal Center. I enjoyed the workshop earlier today, the State of the Science workshop that was hosted in Gainesville. So this is going to be an extension of that and a little more in depth into our climate and the current trends and variability and just what we've been experiencing, mostly focused on the state of Florida. So with that, I'll go ahead and pull up my slides. So give me just a minute. All right, I think we're good to go.
Looks good. Yep.
Okay, and so here's my cover slide. I'm sorry, a gratuitous picture of me enjoying fishing, where we've been living part-time at St. George Island here off the Florida Panhandle coast. But there's a little message behind this photo, is that in spite of recent and projected changes in our climate, our atmosphere and our climate are still ideal for thriving ecosystems, agricultural production, and even human habitation. So we've got an amazing climate and weather system and atmosphere. So basically, let's not blow it, is one of my soapbox moments. But with that, I'll go ahead and get into kind of the heart of the talk. A little more introduction is that I'm going to frame this presentation in terms of weather and climate risks or threats. I've got half a dozen listed here. These are the primary threats for us here in the Southeast United States. They include changes in temperature and also particularly extreme temperatures, changes in rainfall or extreme rainfall and flooding. On the other side of the coin, there's the occurrence of drought, which is also just a natural part and recurring part of our climate here in Florida in the Southeast. There's also sea level rise. And of course, we all know about the threat from hurricanes and tropical storms and severe weather, tornadoes, hail, damaging winds, etc. Now, another soapbox moment is that I've identified these 6 different climate and weather threats, but none of them are new from climate change. These threats have existed all along, and at times we as a society have struggled to deal with these threats. So climate change is not bringing any new threats, but it is changing the nature of them, their frequency, their severity. So that's something we have to be aware of. So with that, we'll go ahead and dive in a little bit more introduction though. I know risk analysis would be horrified by this threat, but by this slide, but it's a very simple model of defining risk, whereas the threat or the probability of an extreme event times the exposure or your vulnerability or the impact that it has. And this can be represented by this simple little graph on the bottom left. Where we want to be is in that bottom left corner with a low probability of extreme climate or weather, and also low impact. We don't want to be up in the upper right corner. But the only way to change our position on this graph, as I'll show you, the probability or likelihood of these existing weather and climate threats is not likely to go down at all. In fact, it could be going up as climate change progresses and we go into the 21st century. So the only way to move to a more favorable position is to lower our vulnerability or our exposure. And over on the right, here's an example of that. It's an iconic picture from Hurricane Michael when the storm surge made a landfall in Mexico Beach, Florida. City blocks were just leveled by the storm surge, except for this one structure. And this was built by a retired engineer. It was designed to nearly double the building codes, and it weathered the storm very, very well. So that's an example of moving your position on this graph. However, I would maintain that building a multi-million-dollar structure is not necessarily an accessible way of coping for middle-income families or folks that have lived on the coast for generations. And one more bit of background is we got to talk about the burning of fossil fuels and the accumulation of greenhouse gases in our atmosphere. Here we have the world famous Keeling curve. It's a very accurate measurement of carbon dioxide concentrations taken on the top of Mauna Loa in the Hawaiian Islands, a very pristine location, not influenced by nearby cities or industrialization. And what we see here is from the early 1950s, when this record began, we see a very steady or even exponential increase in carbon dioxide concentrations in our atmosphere, beginning at around 315 parts per million. It's estimated that before industrialization, it was as low as around 280 parts per million. This graph is a little dated. Now we're well above the 420 parts per million threshold and no slowdown in sight. Even more alarming is on the bottom right, I have a graph that's taken from ice core data from Antarctica. And by drilling these ice cores down thousands of feet in the Antarctic ice cap and extracting the air bubbles that are trapped within the layers of ice, scientists have determined the concentrations of carbon dioxide and other greenhouse gases going back almost 1 million years, 800,000 years. And you can see the concentration changes as we go through ice ages and warmer interglacial periods. Concentrations tend to be at their lowest level during the ice ages. But then on the far right of the graph, you can see what's happened in the last century due to human activity and the burning of fossil fuels. So where we are now at 420 parts per million, concentrations have never been high in the previous million years or more. So this is kind of the grand experiment we're doing to our planet. And I'm concentrating on carbon dioxide here. There are other greenhouse gases, methane, nitrous oxide, but by far carbon dioxide is the most plentiful in our atmosphere, and it has the longest lifetime in our atmosphere. So we're really going to concentrate on that. So with that, we'll go in and take a look at temperature trends. I think we've all seen this graph or a similar graph. It's the annual global average temperature since 1880. And there's about 4 or 5 centers around the world that track that from all the historical observations, augmented by satellite and other observations. But they're all very similar to this graph from NOAA and CEI, which shows since about 1900 or the early 20th century, a steady increase in global average temperature to where now we're running at nearly 1 degree Celsius above the historical average. So we've seen talk of trying to limit global warming to 1.5 or 2 degrees Celsius. Well, we're rapidly approaching that 1.5 threshold as we speak. And also what you'll see there is the last 8 years have all been the warmest on record. 2016 is still the record setter due to a very strong El Nino in the Pacific Ocean. But in the last 3 years, we've been in La Nina conditions, which tend to cool the global average temperature, but they're still running at very high levels. So again, that's what we're doing to this atmosphere. What's also interesting is it's not uniform across the globe. Some places are warming more than others. Of course, the Arctic is warming 3 or 4 times the rate of the global average. But if we look at this map of 20th century warming on the bottom right, this is from the U.S. National Climate Assessment, we see that the Western U.S. warmed a lot more than the Southeast, and actually parts of Mississippi and Alabama and parts of the Southeast actually cooled during the 20th century, especially the latter half of the 20th century. And this was known as the global warming hole, if you will, because it was the one spot on a global map that was blue instead of red. But as I'll show you in the upcoming slides, since we've gone into the 21st century, that hole has closed rapidly. Here's some more recent temperatures. And here, both in map form and on the graph on the bottom left, what I'm showing is average annual temperature that's been smoothed by a 5-year running mean, but this goes back to 1895. And what it shows is parts of Florida and the Northeast, the last 5 years have been by far the warmest on record. And if you look at the graph on the bottom left, it shows the Florida statewide average temperature, again, smoothed with the 5-year running average. But if you'll notice, since about 2015, we're now running a full 2 degrees Fahrenheit warmer than any other 5-year period on record. So rapidly in the last 10 years or so, Florida has really caught up with the rest of the nation and the globe as far as seeing this warming trend. In fact, only 7 months out of the last 8 years has the statewide average temperature been cooler than normal. That included a streak of 31 months or almost 3 years in a row with nothing but above average temperature, 9 months of record warm. And interestingly, and I'll show you more on this, it's the overnight temperatures that are affected more than the daytime high temperatures. A snapshot of what's going on in 2023. This is the historical ranking by weather station of temperature since January 1st or year to date. And we see most of Florida, a lot of number ones where all these stations are experiencing their warmest first half of the year on record. A lot of number twos also. The rest of the Southeast still ranks pretty highly. The Carolinas were running number one until a recent cool spell, but Florida still, we're on pace for our warmest year ever. But we've been concentrating on changes in the average temperature where one might think, oh, what's a degree or 2 degrees of change in the average temperature? Is that really that big a deal? Well, it's not just the average that's changing, it's the whole distribution of temperatures or probability distribution. And it can be represented by this bell-shaped curve. And you see as this bell-shaped curve or this distribution moves towards warmer, you get amplified changes in the extremes. Much fewer extreme cold events, much more common extreme heat events. So the extremes are where the real risk lies, and this overall change in temperature is going to have amplified effects on the extremes. And we have other things going on in addition to greenhouse gas and the overall warming trend. There's also land use and land cover changes that affect local climate. And probably the most well-known of that is the urban heat island effect, where all the development, concrete buildings, asphalt, actually hold a lot more heat than the surrounding natural surrounding. And this is from a study from Marshall Shepard at University of Georgia that shows that Southeast Florida metropolis area is actually the area of the United States most affected by this urban heat island effect. And in fact, I just read an article this morning in the Miami Herald, a new study where citizen scientists placed thermometers all over the Miami urban area, and they showed that the heat that they're experiencing in these highly urbanized areas is even greater than the increase in heat seen at the official weather station at the airport. So let's talk a little bit about extreme heat and human health. I think we're all familiar with heat index, which is just a way of combining heat, the effects of heat and humidity on the physiology of the human body and also livestock. And again, picking on Miami, this was done by Brian McNulty at University of Miami. We see different thresholds of heat index, 90, 95, and 100. But all these thresholds, we're seeing an increase in the amount of time at these dangerous thresholds, especially since 2000. And you see the greatest increase in the lower thresholds, not as much increase at over 100 degrees. There's also another measure of that's used to monitor heat stress on humans, and it's called wet bulb globe temperature, where in addition to combining the effects of temperature and humidity, it also factors in wind speed. Higher winds, we get more cooling on our body, and solar radiation, or the amount of direct sunlight. So all this goes into wet bulb globe temperature, which is being used more and more in sporting activities, outdoor occupations, to really manage, to really monitor the threat to exposed humans. And I don't expect you to take much from this chart, but this is done by a consultant to the U.S. military, and it just has different thresholds of this wet bulb globe temperature and recommended activity, or the amount of breaks a person would need. And pay really close to the yellow, red, and black thresholds. That's where we get into really significant danger. So with that, the Southeast Regional Climate Center in North Carolina, Chapel Hill, have done a lot of work with wet bulb globe temperature. They developed a climatology of where it's highest, or where it's most often at dangerous levels across the Southeast. And you'll see really the hot spot is Mississippi, Alabama, Louisiana, where it's really just warm and humid all summer long. But you'll also notice in the state of Florida, there's more days at these danger levels in North Florida than in South Florida. So that's an interesting kind of geographic fact that I'll go into in just a little bit. In fact, on my next slide, this shows what is the average hottest day of the year across the tri-state area and the peninsula of Florida. And, you know, people who don't live in the state might think, oh, further south you go, the more heat you're going to get. Not necessarily. It's actually North Florida, South Georgia, South Alabama are more prone to these extreme high temperatures, whereas South Florida, with the easterly trade winds and the sea breeze and being surrounded by water, has fewer occurrences of extreme high temperatures. And we can look at that, look at days of extreme heat, again at the Miami airport. The top graph shows the number of days where we reach 95 degrees or higher. And you see that number of days back in the 60s and 70s, we would often go a whole summer without seeing 95 degrees in Miami. Now it occurs almost every year, and the number of days is increasing. But if we look at another threshold, 100 degrees, that's a kind of one of my favorite trivia points. Miami has only seen 100 degrees once, and that was in 1942. That's the only recording of triple digits at the Miami airport. So that's kind of an interesting fact, and it just shows how the extreme heat is kind of modulated, again, by the trade winds and being surrounded by water. Now let's talk about the rise in nighttime temperatures. And over here on the right, I show a graph of summertime, nighttime minimum temperatures in the North Florida area from 1895 through the present. And you can see the average summer nighttime temperature was pretty stable until we hit about 1990 or so. And since 1990, we've seen an increase of 2 to 3 degrees Fahrenheit in the average overnight temperatures. So this has big implications. Elevated soil temperatures. I've heard anecdotal reports from farmers and producers that yields are actually down, and they're blaming the warm overnight temperatures. Elevated soil temperatures, cumulative stress on livestock, cattle, poultry. And again, the threat to human health is the human body needs the nighttime coolness in order to recover from the stress during the day. Well, the nighttime temperatures are rising and you don't have air conditioning, it's going to create a lot more problems. And of course, we're talking about vulnerable populations, agricultural workers, construction, sports and recreation, even prison populations. I just learned this last year that 70% of Florida's prison population is unair conditioned. So again, another vulnerable population. And just another illustration of the increase in these warm nights. And this is from the U.S. National Climate Assessment. Again, here we show the number of nights each year at the Miami airport where the temperature never falls below 75 degrees Fahrenheit. And that's what the climate assessment terms as a warm night. And we see back in the 40s and 50s, averaged even under 50 of these warm nights a year. Now in the 2000s, we're up to 150 or more of these warm nights per year, or a threefold increase. Now we'll switch gears and just talk briefly about extreme cold. Here, this is from a book from John Attaway at University of Florida, where he identified a dozen or so what he called impact freezes that had catastrophic effects on the Florida citrus industry. And interestingly, this picture over on the left was prior to the 1894 and 1895 freezes, where this mature citrus grove had trees that hadn't been damaged by frost or freeze for several decades, and you can see how big they are. Well, and also Northeast Florida, the St. Johns River area used to be one of the centers for citrus production in the state. Well, then in 1894, or that winter, December of 1894, February of 1895, some really catastrophic freezes killed the plants to the ground and pretty much ended citrus production on a large scale in Northeast Florida. You'll see there's another cluster of freezes from 1977 through 1989 that pushed the citrus industry even further south of Orlando now, where it's currently kind of centered around Immokalee in the Southwest Florida area. So that kind of chronicles these damaging freezes. One of my favorites was still February of 1899, known as the Great Blizzard. Iconic photo of us legislators having a snowball fight on the steps of the old Capitol in Tallahassee. Measurable snowfall from the Panhandle to Tampa to Jacksonville. Key West and Jupiter, Florida were the only cities east of the Rockies that did not experience freezing temperatures. And open question, is a cold snap of this degree still possible? Okay, a little more quantitative look at extreme cold. Again, picking on the Miami airport, this is the number of days each year where the temperature falls to 40 degrees Fahrenheit or below. And again, back in the 60s and 70s, used to be a fairly common occurrence almost every year. Our last really extreme winter was in 2010, where we had 7 days of 40 degrees or less in Miami. But since then, we've only had 1 day since 2010 of 40 degrees or below. And that even includes this past year, where we did have a late December Arctic outbreak, temperatures below 20 degrees across much of the Panhandle, below 30 across much of Central Florida. However, even with this one cold snap, Miami still did not go below 40. All right, now we'll shift gears and talk about trends in rainfall, which are a little bit more difficult to quantify. Here's kind of a large scale view. This is a map that compares, in the climatology world, what we consider normal is a 30-year average, and they're recomputed every 10 years to best coincide with the current climate. This map compares the previous 30-year normals that went through 2010 with the current 30-year normals of rainfall that go through 2020. And just the difference in these normals, we see an increase in rainfall across much of the eastern United States, while we see a decrease in rainfall in the Southwest and California, Nevada area. So we have kind of seen this overall trend. Whether that can be attributed to climate change or not is still uncertain. But looking at average rainfall can be misleading also, and this is a great example. This is growing season rainfall from May through September for the climate division in South Georgia, which a lot of row crops, cotton, it's the peanut belt, a lot of corn, a lot of row crops grown there. And this shows just annual growing season rainfall since 1895. And you see tremendous year-to-year variability, where you can have as little as 13 or 14 inches during a season, or as much as 33 inches. But tremendous year-to-year variability, but no real trend. And you'll notice that the average is about 23.5 inches per growing season. And that should be enough to make a good peanut crop. But even when you do get that much or more, often the problem is in the timing. In the bottom graph, it shows the water use by peanuts, where when you get into the dog days of summer, where they're reproducing and pegging, then they require up to 2 inches per week in order to stay productive. And so if you get a 10-day dry spell during that critical time, you're in trouble, even if the seasonal rainfall is close to normal. So with that as a backdrop, one thing that the science is observing is an increase in extreme rainfall or very heavy rainfall events. And again, this is from the U.S. National Climate Assessment. It shows the number of days where with 3 inches or more of rainfall for the Southeast region. And you see a pretty steady increase since the 1900s in these heavy rainfall days. So that's what the National Climate Assessment tells us. From years with working with farmers and agriculture, they tell us the same thing, that they're getting more rainfall in fewer events. And it was causing a lot of problems, erosion. If you got more than 2 inches in a day, you lost a lot of the rainfall to runoff rather than infiltrating into the deeper levels of the soil. So here's the solution. They plant very heavy cover crops in the winter months. And then in the spring, they'll terminate the cover crops, roll them down, and do conservation tilling right into this heavy thatch of mulch. And the benefits are myriad. It helps keep soil temperature down. Again, it captures the rainfall that does fall and helps it infiltrate into the soil rather than run off. More organic matter in the soil, more healthy array of microbes in the soil. Just the benefits are numerous, in addition to making it more climate resilient. Now we'll take a look at the other side of the story, and drought or lack of rainfall. And this is where I'm going to introduce climate variability and the El Nino La Nina cycle. And I think most of us are familiar with this El Nino La Nina cycle. Every 2 to 7 years, this area of the Pacific Ocean along the equator can turn several degrees Celsius warmer than normal during the El Nino events, as shown here in satellite renditions from 1997 and 2015. But at the same time, the opposite phase can occur, where that same area gets several degrees colder than normal. And that's called the La Nina phase. And we've actually had been in the La Nina phase on and off for the last 3 years, especially in the winter months when it affects our weather the most. And just to show you a schematic on how that occurs, when we have this anomalous ocean temperatures, it tends to feed back into the upper atmosphere and modulate our average jet stream positions across North America. And this is the typical wintertime setup when we have the La Nina phase, where the storm track is kind of up the Ohio and Mississippi River valleys, but the southern tier of the United States, especially the northern Gulf Coast and the peninsula of Florida, remain warmer and drier than normal. And just month by month, you can see the average rainfall departures from normal, 20 to 30% represented by the brown and yellow shading. So this is typical of what we get with La Nina, where the opposite phase, El Nino, usually brings more winter rainfall than normal and more storminess. Another interesting fact, this is just a graph of sea surface temperatures in that region of the Pacific Ocean, where we can keep track of the coming and goings of El Nino and La Nina. Here, the red spikes are where the ocean temperatures are much warmer than normal. You can see 1998 and 2016 really sticking out as strong El Nino events. But you can also see when it's cooler than normal or the La Nina events. What I really want to point out is the El Ninos tend to occur only 1 year at a time, where the La Nina events can occur 2, 3 years, multiple years. And it's this multiple years of warmer and drier than normal conditions can often set the stage for widespread and multi-year droughts, especially in Florida and in the Southeast. And here I'll just illustrate that. This shows the percentage of area in different categories of drought for South Alabama. I chose them for this illustration. And you can see back in the early 2000s, also 2010 through 2012, 2007-8, you can see where these multi-year La Nina events really correspond almost identically to widespread and severe drought. Except for these last 3 years. Somehow here in Florida in the Southeast, we've largely avoided the development of severe drought on a widespread area. So this was kind of unusual that we had 3 years in a row of La Nina, yet we really never developed the drought that went with it. Well, sneak peek, we've done a rapid transition this summer. Now this is the current sea surface temperatures in the Pacific. Very, very anomalously warm off the coast of South America, 5 to 7 degrees Fahrenheit warmer than normal. And now those warmer than normal conditions have spread all along the equator. So I anticipate in a week or two when NOAA comes out with their monthly statement, they're going to declare that we are in El Nino conditions, and it will impact our weather and climate both during the hurricane season and specifically starting in October or November. We should start to see enhanced rainfall and more storminess from these developing El Nino conditions. And shameless plug, we are here in Florida, we're very active with the U.S. Drought Monitor and give them recommendations every week. Our office has started doing these infographics where we give a little more detail and just show the thinking behind the current drought map. So now we're really going to switch gears, look at another one of the threats on my list, and that's sea level rise. And sea level rise is nothing new. Sea levels actually rose 150 meters or so as we came out of the last ice age and these enormous continental ice sheets melted. So this graph here goes back 24,000 years. I'd like to call your attention to about 8 to 10,000 years ago. We were still seeing a rapid rise of sea level. And then in the last 4 to 5,000 years, it's really leveled off. But look at that 8 to 10,000 years, and it's significant because archaeologists here at Florida State University did some studies where they found artifacts and evidence of indigenous settlements out on the continental shelf in 50 to 60 feet of water. So what that shows is these communities of Native Americans actually lived near the shore then, and as the seas continued to rise, they followed the coastline inland as more and more coastline was taken away. So humans have dealt with sea level rise before, but let's talk about more modern times. That's where it's getting really critical. And just a quick review, the causes of sea level rise, there are 2 primary causes. And one is, and still the majority of sea level rise is from the thermal expansion of ocean water. as the oceans heat, especially the top 2,000 meters or so, as the oceans warm, they expand. Warmer water takes up more volume. So there's the thermal expansion of ocean water. And the other mechanism is the melting of glaciers and continental ice sheets. And here in the different colors, you can see the contribution from Antarctica, Greenland, other glaciers. It is not from the melting of sea ice like covers the Arctic Ocean. That's already on top of the water and has already displaced the same volume of water. So the sea ice melting, while it's a problem for ecosystems in the Arctic, it's not really contributing much to sea level rise. So how do we monitor sea level and global sea level and sea level rise? We have two primary tools. One is a network of tide gauges around the world and across the United States coast. Here's a map of all the long-term tide gauges with an arrow showing the trend in sea level at these different locations. And you'll see it's not uniform. Up in Alaska, where they're still undergoing crustal rebound from the loss of ice in the last ice age, the land is rising, so the sea level is actually falling along the coast. Where the opposite, Louisiana, where we're seeing a lot of subsidence from the oil and gas industry, and also just the channeling of the Mississippi River and the lack of deposition now, seeing a lot of subsidence. So their sea level rate of rise is over twice that of Florida. But here in Florida, we don't have a lot of geologic processes going. Here I show the tide gauge at Pensacola, Florida since about 1925. And we see a very steady increase in sea level there of about 2.3 millimeters per year, which corresponds to about 8 or 9 inches per century. And the rest of the tide gauges around Florida and much of the Southeast are similar. The Carolinas and the Outer Banks are seeing actually more of an increase. We also have another tool to monitor global sea level, and that's satellites known as altimeters that very accurately measure the height of the ocean from space. And we've had altimeters up since 1992, so we're getting a longer record that we can do climatological studies on. And one thing it shows us is over on the bottom right, sea level rise is not uniform around the world. The greatest rates of sea level rise are the Western Pacific, where ocean temperatures are at their warmest, along the coast of California and South America, where we have cold water upwelling. The rate of rise is not nearly as much. So that's very interesting. But if we put all these together and also add in projections for the next century, we get a graph like this from the U.S. National Climate Assessment. The black line is the historical record from these tide gauges. The little red line is where we add in the satellite record since 1992. And then the divergence of lines are the various projections and under different emissions scenarios. And some important takeaways here is we are starting both in the satellite record and the tide gauge record to see an acceleration in the rate of sea level rise. So that's very troubling. And you can see it here if you look closely at this graph. But also, you see a wide range of uncertainty in the projections going out into 2100, anywhere from a continuation of the current rate, which would put us at about another 1.5 feet or so by the end of the century, to under some of the higher emissions scenarios, a change of 2.5 to 3 meters, which would be 6 to 8 feet. So a lot of uncertainty there. I think we can rule out some of the highest emissions. Those don't look realistic at this time. But another takeaway is that bottom scenario, which is just the current rate, that is the floor of what could happen in the next century. We're 100% certain to continue on at least the current rate or higher. And say we say one of these lower scenarios or lower estimates out to the end of the century come to fruition, that still doesn't mean there's not going to be a ton of problems. And this is illustrated. We've all read about the sunny day or just high tide flooding that occurs in South Florida, the Miami area, Charleston, Norfolk, New Jersey, up and down the East Coast. Well, here's an interesting graph from the tide gauge at Virginia Key in Miami, and pay very close attention to that 4-foot level. Prior to 2015, that 4-foot level was only eclipsed when there was a nearby hurricane. And here we have them pointed out, Rita, Wilma, Hurricane Sandy. However, since 2015, that 4-foot level is eclipsed multiple times per year just from the astronomical or king tides. So it's this kind of nuisance flooding that really affecting infrastructure, plans going forward, adaptation, and it's only going to become more and more common as sea level rise progresses. All right, one last topic to hit and then we'll sum it up, and that's hurricanes and tropical cyclones. And to tell this story, I'd like to go back to 2016. Going into the 2016 hurricane season, the state of Florida and also the nation as a whole was in an unprecedented hurricane drought. It had been 10 years since a hurricane of any strength, Category 1 or higher, had hit the state of Florida. At the same time, it had been 10 years since a major hurricane, Category 3, 4, or 5, had hit anywhere in the United States. So both of these were unprecedented in the historical record. But there's an old saying in baseball that you play to the back of your card. Remember when we used to collect baseball cards and they'd have the picture of the player on the front, but then the lifetime statistics on the back? So the message is that a player goes through hot streaks and slumps, but over the course of a long season will be close to his lifetime average. Well, the same thing with hurricanes. Florida broke the streak with Hurricane Hermine in 2016 that affected the Tallahassee area. That was followed by Hurricanes Harvey and a slew of hurricanes that hit the northern Gulf Coast. Hurricane Irma that affected the whole state of Florida, Maria. So Hurricane Michael, it's been nonstop since we ended that drought. And just recap of some of the recent hurricane seasons, they due partly to La Nina conditions in the Pacific Oceans. We've had 3 very active seasons in a row. The 2020 was a record breaker with 30 named storms. And interestingly enough, 10 landfalls on the Gulf Coast, which really have a big impact on the Southeast United States. 2021 was not quite as active, but still above average, and still 6 landfalls on the northern Gulf Coast. Now, 2022 was also forecast to be above average in hurricane activity, but ended up being pretty close to normal. However, it only takes one, and we had Hurricane Ian that really devastated the Fort Myers area and much of the state of Florida. So what can we say about how climate change is affecting the occurrence of hurricanes and tropical cyclones? Well, on the top left is a graph of, this is not just the Atlantic Basin, but this is globally. There are hurricanes in other basins, the Indian Ocean, the South Pacific. This shows the number of tropical storms each year on the top line and the number of hurricanes each year globally since 1970. And you see there is some year-to-year variability, but really the average number remains relatively unchanged. And with modeling studies also, that's kind of the consensus opinion, is that hurricanes and tropical cyclones will not necessarily be more frequent. However, what we can say is the stronger hurricanes are getting stronger. Jim Elsner here at FSU has shown this years ago and continues to study how the very strongest storms of each season are getting stronger. Modeling studies support this. There's a measure called hurricane potential that combines the amount of fuel for a hurricane from warm sea surface temperatures and also a warmer and moister atmosphere, that the amount of potential or the ceiling to how strong a storm can become is increasing and will continue to increase. Other observational studies show there's increasing rainfall from tropical cyclones, that a moister and warmer atmosphere holds more moisture, which is then available to be released in rainfall from a landfalling system. Rapid intensification, where a storm gains at least 30 miles per hour in strength in under 24 hours, is becoming more common. And we've seen that with Hurricane Michael and Harvey and a number of landfalling systems in the last few years. And this is especially problematic when it happens just prior to landfall. It creates a forecasting nightmare. Also, other studies show forward motion may be getting slower, which again would prolong the impacts at landfall, and that tracks may be shifting further north in latitude as the climate and the oceans warm. So one last slide, though, there is a climate variability or year-to-year changes in hurricane activity, and a lot of those can be attributed to the phase of the Pacific Ocean. And this is just from an old study we did at this center. It shows the probability of having 1, 2, or 3 or more hurricane strength landfalls in the U.S. And what we see is the likelihood of at least one is pretty high in all 3 phases, both the warm or El Nino phase or the cold La Nina phase. However, when we get to 2 or more hurricane landfalls, when we have a lot El Nino in the Pacific Ocean, it tends to create an unfavorable environment of upper level winds over the Atlantic basin, and we get less storms. So the likelihood of 2 or more during an El Nino is only around 30%, where it's up to 65% or more during the La Nina phase. So that's a change in probability of nearly double, just depending on the phase of the Pacific Ocean. So with that, I'll go ahead and summarize, and we'll just take a quick look back at our different weather and climate threats and what we can say, both from observational and modeling studies, on how climate change is affecting them. And I have them listed for what we're more certain or what the science supports most strongly, to where there's a little more questions and a lot more research that needs to be done. Sea level rise, like I said before, it's nearly a certainty we're going to continue at least the current rate. Studies show that that rate is accelerating, likely range by 1 to 4 feet by the end of the century. Temperature, very likely to continue rising with increasing greenhouse gas concentrations. Maybe Florida will be less than interior North America because we're surrounded by water, but the past decade has showed us that no, we're not immune to these sharp rises in temperature. Drought, it's really hard to say what the changes in annual or seasonal precipitation will be in different regions of the country or the world. The climate models really don't handle rainfall as well as they do temperature. But some things we can say about drought is, even if rainfall patterns remain relatively unchanged, rising temperatures alone change the whole water balance equation and evapotranspiration. So rising temperatures alone could lead to more frequent and more prolonged periods of drought. With rainfall, both modeling studies and observations show that we are getting more extreme rainfall events or more rainfall in these extreme events. Again, changing seasonal or regional patterns are a lot more uncertain. And we just went over hurricanes, so I don't need to repeat that, but I think that about finishes up, and we can go to the question and answer session.
Well, David, thank you so much for that wonderful presentation. And I do just want to remind everyone briefly that today's presentation is recorded. For all of you that registered, you'll receive a notification when that's ready. If you ever want to refer back to anything that was said today. And as David said, yeah, we do have a few minutes for some questions or comments. Once again, use the Q&A for that, and I'll be monitoring that. I'll give everyone just a couple of moments to kind of collect your thoughts and type in any questions. You'll just go ahead and type those in. Like I said, we'll give everyone just a couple moments, so feel free to put in those questions or comments.
While we're waiting, I'll pass along a story from my old boss and mentor, the very esteemed scientist James J. O'Brien, who was here at FSU. He had a great trick for these kind of presentations. He said to stage a friend in the audience with a question that you know what he's going to ask and you have an answer prepared, but that first question really gets the ball rolling. And so that's a great trick that I sometimes still use.
That's a funny story. And yes, I think we can all relate to that. Okay, so there was a comment from Barbara McAdam that she's going to share the presentation. So thank you so much. Michelle Cooper said, can you repeat the back of card analogy? It was great.
Okay, yeah, I don't know if baseball cards are still a thing anymore, but you know, when I was a kid, some people collected baseball cards, and like I said, the card would have the picture of the player on the front and then his lifetime statistics on the back. And the saying was, a player will play to the back of his card, meaning he could go through a really hot streak or a slump, but over the course of a long season or so, he's going to be pretty much what his career averages say he is. And so I was using that as an analogy for that hurricane drought, that even though that did occur, that didn't mean that climate change was making fewer hurricanes. It was just a statistical fluke.
Great, good point. There's a question in here, David, about Saharan dust and how it during a prolonged period last year, which dampened rainfall in August in Miami-Dade area. Do you know anything about that?
Yeah, what I know is when we have these Saharan dust events, you know, they can make their way all the way across the Atlantic, and doing so, they affect the main hurricane formation region off the Azores too. And what it is one, the weather that creates these episodes of Saharan dust tends to be warmer and drier and causes really stable layer in the atmosphere. But also the dust itself absorbs sunlight and even furthers that warm, stable air layer in the atmosphere. So it helps inhibit hurricane and tropical development, but also if it makes it all the way to Miami, it can inhibit just the usual afternoon thunderstorms also. So yeah, that is something that forecasters look at. They monitor the Saharan dust and kind of gives them a heads up on what might or might not be a more active period during a hurricane season.
So there's another question, and this may be the last one as we're closing up today. And it's from Jarek, and it says, could you briefly go over citrus retreating from North Florida again? There were freeze events at the end of the 19th century, but yet the citrus tend to thrive into the 20th century.
Yeah, no, especially around the Jacksonville area, the freezes of 1894, 1895, 1899 really did catastrophic damage. So while some groves might have replanted and been able to continue their operation, the widespread citrus production was really kind of ended during those freezes. And then again, the areas north of Orlando, like Dover and stuff, they really suffered a lot of damages in the 1980s. So that contributed to the migration of the citrus industry. Also, just pressure from development and such contributed also. But that kind of leads to an ongoing question: is with a warming climate, will citrus production become more viable in further north up the state? We still had a pretty good cold snap last year in North Florida that would have done a lot of damage. So there's still going to be risk involved, but it could be changing production. Yes.